And before I start, I want to acknowledge my colleagues who also worked on this project. Kim Scott was our project manager, and Jason Brown and Eric Culbertson are data scientists at Australia, and they all did a huge amount of work on this project. So part of this project motivation was actually that I needed a practicum project to complete my master's degree. But we also wanted to explore change detection and the effects of climate change and food insecurity in a country that may be in need of food assistance programs using remote sensing imagery and machine learning. And climate change is expected to increase the prevalence of malnutrition in the 21st century through higher temperatures, increasing rainfall volatility, and weather extremes that could have devastating effects on crops and freshwater availability. So we wanted to explore this a bit and see how machine learning and remote sensing imagery could help the situation. And at Australia, we specialize in applying machine learning to satellite imagery, and we've developed a geospatial machine learning platform called Earth AI to handle the volume and complexity of remote sensing imagery. We chose Zambia as our area of interest because they're ranked as 5th worst in the Global Hunger Index, and they've been severely impacted by climate change. And we intentionally selected a politically stable country to control for confounding variables such as war or economic sanctions, so that the food insecurity issue is really a result of weather extremes that affect crops slowly over time, rather than a result of a volatile political environment, which could be beyond the analysis capabilities of remote sensing data. In Zambia, agriculture supports the livelihoods of 85% of the population, and it's a landlocked country where most farmers rely on rainfall to irrigate their crops. So it's especially vulnerable to weather fluctuations. Because of its global coverage and long archive of free and publicly available data, we decided to use Landsat 8 imagery in this project. This satellite revisits the same spot on Earth approximately every 16 days and produces imagery at a spatial resolution of 30 meters in the visible near infrared and shortwave infrared spectrums. And we quickly discovered that a ground truth geo-referenced crop data set is hard to find, if not impossible, for most of the world. But luckily, the USDA has produced one annually for the continental United States since 2008. And this data set is called Cropscape, and it labels 92 different crops and 25 land cover types at 30-meter resolution. So we decided to use the Cropscape dataset to train our model in the US, and then we extrapolated the model to Zambia. But to do this, we really had to select regions of the US as our training data that mimicked characteristics of Zambia to create a representative training sample. Using some basic statistics about crop production in Zambia, we've figured out the most common crops according to the number of hectares planted and the yield of each crop in 2015 and 2016, using a few different crop statistic data sources that we found. And we had to skip over cassava, which is the second most abundant crop in terms of area planted, since it's very rarely grown in the US, so it wasn't included in our training data set. And in total, we included 9 crop types in our model, since cotton shows up in both lists. As I mentioned before, we used our own in-house machine learning platform to perform the data processing and modeling for this project. The Australia Earth AI platform is built on Apache Spark and Amazon Web Services infrastructure. So it's scalable and distributed, and the amount of imagery we need to process for this modeling effort was almost a terabyte. So Earth AI allowed us to perform the modeling in a timely and efficient manner. The first step in our modeling process was to read in the Landsat 8 imagery and ground truth Cropscape data and spatially join these 2 raster data sets by reprojecting and resampling the ground truth to match the remote sensing data. We derived a whole bunch of water, vegetation, and soil indices from the raw Landsat 8 bands to use as features in our model. Then we exploded the raster data into pixels, so each row in our data set is a pixel and the columns are different bands. because that's how Spark expects the format of the data to be in. We use the Landsat 8 quality assessment band to filter out bad data, such as pixels covered by clouds. And we created the time series features by averaging each of the spectral features by month. Then we split the data into train and test sets and train and evaluated a classification model. And finally, we scored the model over Zambia across 2 years, 2015 and 2016, and we performed post-classification change detection on the model predictions. Because not all of the crop calendars of our chosen crops were in sync, we decided to have 2 separate models for summer and winter crops. In the region of the US that we were using as training data, sugarcane, potatoes, and wheat are winter crops, while corn, cotton, peanuts, millet, and tobacco are summer crops. Whereas in Zambia, the crop calendars are opposite since it's a different hemisphere. For both the summer and winter growing seasons, our best performing model was a gradient boosted trees. So that was our final model for both. In this summer model, millet had a poor recall, as you can see, compared to the rest of the classes, because our training data set was unbalanced. So we had too few examples of this class. And in the winter model on the right, this model performs better than the summer model in terms of accuracy and F1 score. And we thought that was probably because there was fewer classes, and maybe that the barren winter landscape just made these classes easier to model than the summer classes. We scored the summer and winter models over Zambia across 2 years and performed post-classification change detection on areas within Zambia. And through this, we were able to detect changes in natural resource accessibility, as well as track crop availability and rotation over time, and kind of get a sense of food insecurity in the region. This is one example. We were able to detect a significant reduction in the water levels in the Meta Hills freshwater reservoir between 2015 and 2016. And here's another example. We were able to track a shift of dominance of corn and peanuts to tobacco crops in this district in Zambia between 2015 and 2016. And this is actually showing a shift of food crops to cash crops, which would generate more income in times of need since they're grown for sale instead of consumption. So we actually spent a good amount of time just visualizing our model predictions because it really helped to pinpoint the changes and identify areas at risk. One of the biggest challenges with this project was model generalizability, since we were training the model on the US, but scoring it in Zambia. To help with generalizability, we tried to pick regions in the US to use as training data that had similar characteristics to Zambia, as I alluded to before. So we compared climate, biome, weather patterns, soil composition, the mix of crops, and we tried to just make it as much of an apples to apples comparison as we could. But in the end, we were still extrapolating to a different region in a different hemisphere, and that is always challenging. Zambia has a tropical climate, which means they have rainy and dry seasons rather than cold and warm like what we have, which affects how crops grow. And also one thing we noticed was that the way they plant crops in Zambia is not really the same as it is here, because their farmers tend to have smaller fields of mixed crops. And there's a lot of small gardens which are meant to support 1 or 2 families. Whereas in the US, our crop fields tend to be very large and homogeneous. So these differences made it really hard to generalize the model. Another challenge with this project was just the enormity of remote sensing data that needed to be processed. Luckily, our distributed platform sped up the processing time and mitigated some of the challenges of working with geospatial data. We used optical imagery in this project, which meant that we had to contend with clouds. If a cloud covered a specific pixel at any time throughout the growing season, then that pixel was dropped from our data set. So we lost a lot of data this way. And we had a couple of crops that were already pretty rare in our data set, like millet. So millet didn't perform very well in the final model. So this led us to start investigating different ways of reducing missing data. And one of the most promising techniques was incorporating a synthetic aperture radar, also known as SAR, data into our model. And for those of you that don't know, SAR is a form of radar that works by transmitting microwave pulses down to Earth. And the pulses are reflected or scattered when they come into contact with an object. And then they return back to the satellite where a sensor makes an image from the returned echoes. And the reason SAR is so useful is because a typical satellite has a passive optical sensor that requires sunlight to illuminate an object. But since SAR doesn't require sunlight, it can sense during the day as well as night and produce a lot more imagery. And another big advantage of SAR is that microwave pulses are able to penetrate clouds. So SAR can produce imagery even on cloudy days, which makes it really useful for missing data. As shown here, we've had some promising initial results combining SAR with optical imagery to classify crops. So in summary, as climate change continues to alter weather patterns, countries affected will have to adapt to different growing seasons and weather patterns. So a model that allows people to visualize the changing distribution of crops and water over time will help countries adapt, as well as identify areas at high risk of food insecurity that need help. And that's the end of my presentation. Our website is straya.earth if you want to check us out. And if you have any questions, I'm happy to take them if I can figure out how. I'm also going to be in the, I'll pop over to the networking lounge after this so I can answer any questions there too.